Okay, good afternoon, dear students. In yesterday's class, we discussed about the specific conductance, equivalent conductance, and molar conductance. Meaning is conductance. In today's class, I am going to discuss about the effect of dilution on conductivity and another the Coldrack's law and application of Coldrack's. First one, the effect of dilution on conductivity. The effect of dilution, the effect of dilution on conductivities. When you take any of the electrolyte, you are adding the water, the distilled water, when is diluted, then dilution, what is the effect of conductivity? When the solution is diluted, when solution is diluted, concentration is decreases. The electrolyte concentration is decreases. What happens? Conductivity here, the specific conductance and equivalent conductance and molar conductance. What happens? On dilution. The effect of dilution on conductivity here. And the electricity is carried by the ions here. The electricity is carried by ions. Electricity is carried by ions. When presence of ions, the electricity is carried here. It conducts electricity. Electricity is carried by ions. The conductivity of a solution depends upon the number of ions here. The conductivity of the solution is depends upon the number of ions present in the solution. The number of ions present in it. As the volume increases, the concentration of the electrolyte is decreases or the solution decreases. The concentration of the solution decreases. Here the volume is increases. Volume is increases and the concentration of the solution decreases and the concentration of the solution decreases. When you take a solution and you are adding some volume of solution and you are adding the distilled water. When solution is diluted, then the concentration of the solution is decreases here, and hence the dilution increases. The number of ions does not increase. Here, the dilution increases, but here the number of ions does not increase, and in the same proportion. Here, dilution increases and the number of ions does not increase. Does not increases with the same proportion. With the same proportion. With the same proportion. When you are adding the solution, when dilution is increases and the concentration of the solution decreases and dilution is increases and number of ions does not increases with the same proportion or with the same number. Here increase the same proportion, that is the number of ions per cc of the solution decreases here, that is the number of ions the number of ions per cc. Cc means here ml per cc of the solution decreases. Per cc of the solution decreases. See here dilution is increases, number of ions does not increases with the same proportion but that is the number of ions per cc of the solution is decreased. Number of ions is decreased per cc per ml per cc of the solution is decreases, and here the specific conductivity depends upon the number of ions per cc of the solution. Here the specific conductivity is depends on this the per cc of the solution. Here the specific conductivity depends on the number of ions per cc of the solution or per unit solution or per unit solutions. This the specific conductivity depends on the per cc of the ions. Here per cc of the ions present in the solution or present in a per cc of the solution. Number of ions depends on the number of ions. This number of ions per cc of the solution. Per cc of the solution. Here the specific conductance depends on the number of ions per cc of the solution or per unit of the solution or here per unit. This is also the per unit one. Per unit 1. Per unit 1. And then the specific conductance decreases with dilution. Here the dilution is increases. Here the specific conductance decreases and the equivalent conductance and molar conductance increases. Here the specific conductance decreases. Specific conductance decreases with dilution. On about here, the specific conductance decreases with dilution, and the equivalent conductance and the molar conductivity increases upon dilution. Here, the equivalent conductance and molar conductance increases with the dilution. Increases with the dilution. And here, since the equivalent and molar conductivity is the product of the specific conductivity one, here these two equivalent conductance and the molar conductance, these two are the product of the specific conductance and volume. Here these two are the product of the specific conductance and volume. Specific conductance and volume. Here the effect of dilution and conductivity, the electricity is carried by ions. Here the electricity is carried by ions. When the volume of solution is increases, the concentration of the solution is decreases. You take a sugar solution, you add the water, you dilute the sugar solution, the sugar concentration is decreases. And here the volume increases, the concentration of the solution decreases, and the dilution increases, number of ions does not increase with the same proportion, that is the number of ions per cc of the solution decreases here, and the specific conductance on it is depends on the specific conductance of the number of ions per cc of the solution, and the specific conductance decreases and the equivalent and molar conductance increases because of here the equivalent conductance and molar conductance are increased because these are the product of the specific conductance and volume. Here therefore the equivalent and molar conductivity increases on dilution, or as the concentration of the electrolytic or electrolyte decreases here. Concentration of electrolyte means solution here is decreases, and the equivalent and equivalent conductance with the dilution of the some common electrolyte. For example, for this common examples for effect of dilution on conductivity, we draw this and run here we draw for understanding for effect of dilution. Here concentration and here the equivalent conductance, equivalent conductance, equivalent conductance. Here get some points here. And here get some points. This is the acetic acid, weak acid. Acetic acid CH3COOH, and here KCl, NaCl, and here HCl. Okay, this is a diagram, the effect of dilution. This is the graph, what is the concentration versus equivalent conductance. Here this is a potassium chloride, sodium chloride, and hydrochloric acid, and here the strong acid, and this here the weak acid, acetic acid. This is a hydrochloric acid. You taken this example for this electrolytes are taken, and these are the common examples here. As in here in this case of strong electrolyte, it has a tendency to reach a limiting value. To reach a limiting value, you are reaching this some limiting value. That is a strong electrolytes are reach at the limiting value of equivalent conductance at a infinite dilution. Hence, it reached some tendency of limiting value of equivalent conductance at a infinite dilution. See here, this is a infinite dilutions are taken. In strong electrolytes, the infinite dilution is 398. And the equivalent conductance at infinite dilution. Here, this is the infinite dilution. It is denoted as lambda infinity. It is denoted as lambda infinity. Or you write or lambda infinity. This is the equivalent conductance of infinite dilution denoted as lambda infinity. This is capital lambda. This is a small lambda infinity, and by lambda infinity of lambda infinity. It is the equivalent zero conductance is denoted by here. This is a when it is infinite dilution. For zero conductance, the equivalent conductance is denoted as lambda equivalent. This is a zero. Here, this is a zero conductivity of equivalent conductance. Or you can denote lambda here 0 and this is a equivalent. We denote for infinity purpose this one lambda infinity and this is a small lambda infinity. For 0 equivalent conductance this is a lambda 0 and this is a lambda 0. And here for strong electrolytes the value of lambda infinity can be calculated. For strong electrolyte, here the equivalent conductance of strong electrolytes, the lambda infinity value can be calculated. The lambda infinity value can be calculated. The straight line of the graph will be extra floating. Here, this is it comes a straight line for this strong electrolyte use. Example for here, the strong electrolyte. Strong electrolyte, the graph is straight line. The extra plotting the straight line graph is obtained here and the to the zero concentration. Here consider zero concentration. But in case of the weak electrolytes, this is it attained at the limiting limiting values, and for weak electrolyte, for weak electrolyte, for weak electrolytes, there is no indication that of limiting value here. There is no indication of limiting value. See here. There is no indication of limiting values can be obtained here. It is approaches to the zero concentration. Here it approaches the zero concentration. No indication of the weak electrolytes and therefore it is not possible to find the limiting value by the extra property. It is not possible to calculate to the limiting value of the extra protein graph here. And however, there is an indirect method for finding this infinite for weak electrolytes for obtaining equivalent conductance at infinite dilution for the weak electrolytes, which is based on the Colrat's law. Here, when finding the equivalent conductance, it is impossible to find the equivalent conductance when it is used for this purpose. Use the indirect method, that is indirect method for the weak electrolyte. For weak electrolyte, we use indirect method for finding the equivalent conductance, that is the Colrat's law is used to calculate the equivalent conductance of weak electrolyte. The spelling is in right here. This is a whole vaccine. This is the effect of dilution on conductivity. Next, cell constant. Conductance is 1 mark question, molar conductance is 1 mark question, and specific conductance is 1 mark question. The unit and definitions of those terms, and this is also 1 mark important. The cell constant. Cell constant, it is a order to get the value of specific conductance and the value of observed conductance here. In order to get the value of specific conductance and observed conductance, a conductivity should be it is similar with the term L by A is written as L by A here. This is a cell constant, the specific conductance and observed conductance, that is L by A. Here L is the distance between electrodes. L is the distance between electrodes. Distance between electrodes. Here L is the distance between electrodes and A is the area. A is the area. Here L by A. And the term L by A is a constant for a given conductivity cell here. This L by A is a constant for a given conductivity cell, and here L is the distance between two electrolytes here, and A is the area. And here the factor L by A is referred as, this L by A is referred as this cell constant. In this cell constant, formula of cell constant, here the specific conductance is equals to the observed conductance multiplied by L by A, or observed conductance multiplied by cell constant here. And write the specific conductance. The specific conductance is equals to the observed conductance. Observed conductance multiplied by L by A. This is the specific conductance. Here cell constant means this is L by A. Substitute here cell constant. Specific conductance. Specific conductance is equals to observed conductance. Observed conductance multiplied by cell constant. Multiplied by cell constant. You take this side, therefore cell constant is equals to, therefore cell constant is equals to specific conductance divided by observed conductance is equals to specific conductance divided by observed conductance. Observed conductance. This is a formula for cell constant. When you are finding the cell constant value, you use this formula, that is a specific conductance divided by observed conductance. For example, you take the problem on this finding the cell constant value. The vessel here, problem is at 25 degrees Celsius. Temperature is 25 degrees Celsius and the specific conductivity of n by 10, specific conductivity of 1 n by 10 n by 10 KCl n by 10 KCl are 0.1 n KCl or 0.1 n KCl is 0.1 n KCl is 0.00278 0.00278 here. This is at 25 degrees Celsius for 0.1 n KCl. Now the here this is 0.00278. I take another, that is a 0 per ohm. This is a value here. This at 25 degrees Celsius. For first point, you take yourself for problem for finding the cell constant or doing experiment in laboratory. Here, for first point here at 25 degrees Celsius, specific conductance of n by 10, the KCl, this is n by 10 are 0.1 n KCl. Here n by 10 you take here and you value here n by 10 means it is a 0.1 n KCl. 0.1 n KCl here 0.00278 per ohm, and the resistance of this solution placed in this cell, resistance is here, the resistance of this solution placed in the cell is is 500 ohms. And here you calculate the cell constant. Here calculate cell constant. Calculate cell constant. This is the first problem. I will take universal problem in the use in the books, and here calculate the cell constant value. This is a cell constant. This is very important for 1 mark question. Next, Colrex. Colrex law, or law of independent migration of ions, or law of independent migration of ions. Independent migration of ions. This Colrex law is also very important. This is very important for understand the conductivity or conductometer experiment. Here the Colrex law is very important here. When you understood this Colrex law, is easily understood the conductivity experiment. And here the Colrex law, the law of independent migration of ions here from the study of equivalent conductance. Here the equivalent here the study of equivalent conductance of different electrolyte at infinite dilution. Here, see, in Colrat's law, we studied of equivalent conductance of different electrolyte at infinite dilution. That is, infinite dilution is denoted as the equivalent conductance is lambda infinity. Here, the Colrat's law has discovered that the ion contributes here. The ions are contributed here. The migration takes place here. These are the ions here. The migration takes place. This is found or discovered the contribution to the ion contribution to the conductance of the solution. Discovered the ion contribution or ion contributes to the conductance of the solution. Conductance of the solution. Okay, here this is given in 1875. In 1875. In 1875, he initiated a generalization law is called as a Colrat's law. Here, the Colrat's law is states. This is one mark question. State Colrat's law. And I highlight here the Colrat's law. The equivalent conductance of an electrolyte at infinite dilution is equals to the sum of the equivalent conductance of the component ions. This is known as a Colrat's law. This is a statement of Colrat's law. Okay, right here, this statement. Colrat's law. The equivalent conductance of an electrolyte. The equivalent conductance of an electrolyte at infinite dilution that is lambda infinity. Infinite dilution, this is equals to the sum of the equivalent conductance. Here equals to the sum of the equivalent conductance. Sum of the equivalent conductance of the component of ions. Okay, this is a statement for Colrat's law. Here, the conductance of an electrolyte, at infinite dilution. Here, the infinite dilution. See here, the equivalent conductance of an electrolyte. The equivalent conductance of an electrolyte. The equivalent conductance is denoted as lambda. Okay, and here of an electrolyte at infinite dilution. At infinite dilution, here take this is a infinite. At infinite dilution, and here this is equals to the sum of the equivalent conductance. Therefore, here is equals to sum of equivalent conductance. A sum of equivalent conductance. C. You take N C. And answer cations. Equivalent conductance Cl. and sum of the equivalent conductance of the component of ion. Ions means the positively and negatively charged ions. The positively negatively charged, that it is known as a cations. The positively charged ions is a cations, and negatively charged ions is a ion ions. Here ion ions and cations. You can write also you can write this lambda c and lambda a here. And write the lambda infinity is equals to lambda positive sign, and here lambda positive sign plus lambda anions and cations plus lambda negatives. Write this type of you write this type or you write this type. Lambda infinity is equals to, this is positive cation, this is the negative anion. This is the formula of the Colerax law. This is the statement of Colerax law. And where this lambda A and lambda C are the ionic conductance, lambda A and lambda C are the ionic conductance of ionic conductance at infinite dimension, or the ionic conductance at infinite dimension. Okay, see here, this is a lambda infinity is equals to lambda a plus lambda c, or lambda infinity is based on that this formula also, lambda positive plus lambda negative sign. And where the a and c, lambda and lambda c are the ionic conductors at infinite dimension. This is a Colerax law. And next, the applications of Colerax law. Applications of Colerax law. Applications of Colerax. Here there are five applications of Colerax. There are five applications are there. Here first one, to determine the ionic conductance. First application, to determine the ionic conductance. To determine the ionic conductance. Second one, in the determination of lambda infinity, in the determination of lambda infinity, determination of lambda infinity at weak here, the determination of lambda infinity of weak electron, of weak electrolyte, of weak electrolyte. First application is to determine the ionic conductance. Second application is in the determination of lambda infinity of weak electrolyte. Next, third application, the calculation of ionic mobility. Calculation of ionic mobility. Calculation of ionic mobility. Next, fourth application, the calculation of degree of dissociation of weak electrolyte. the calculation of degree of dissociation of weak electrolyte. Degree of dissociation of weak electrolyte. Next, fifth one. This is the last application. Calculation of ionic product of water. Calculation of ionic product of water. Calculation of ionic product of water. These are the 5 applications in Coldrack's law. First one is to determine the ionic conductance. Second one, in the determination of lambda infinity of a weak electrolyte. And third one, calculation of ionic mobility. And fourth one, the calculation of degree of dissociation of weak electrolyte. Fourth one, calculation of ionic product of water. We will see one by one. Okay, I will stop here in class. I will continue these remaining the application of Coldrack's law in next class.